In this video, I'd like to introduce the idea of diagonal matrices and show you how to diagonalize a matrix A using the eigenvectors of that matrix. So we'll consider a 2 by 2 matrix which has eigenvectors given by, it has an eigenvector C1 given by x1, y1, and eigenvector C2 given by x2, y2. So these are the eigenvectors of a matrix A with corresponding eigenvalues lambda 1 and lambda 2. And the defining characteristic of these eigenvectors is if we apply the matrix A to each one of them, we just recover the same vector but scaled by its corresponding eigenvalue. All right. We can rewrite these two statements more compactly as follows. So if matrix A has entries given by A, B, C, and D, then we can combine these two statements into the following. So we have our matrix A. We have a matrix that's constructed from the eigenvectors. So this is our matrix A. This is a matrix that consists of the eigenvectors of our matrix. We again have our matrix of eigenvectors. And this is multiplying a diagonal matrix with the eigenvalues along the diagonals. And you can satisfy yourselves that if you carry out these two matrix multiplications, you'll end up with both of these equations at the end. So this is again the matrix of eigenvectors. And this one is our diagonal matrix, which we'll denote by D. So we'll call this matrix matrix C. So we can write this compactly as saying A times C has to equal to C times D. So that means that we can find the diagonal matrix D by taking the inverse of our matrix C, putting it on the other side, in such a way that our matrix D is given by the following product of matrices. Right, so we can diagonalize a matrix A by a matrix C that's built from the eigenvectors of our matrix A. All right, so a few important notes about this process. So you recall from the previous example that finding the eigenvalues and eigenvectors of our matrix essentially recasts our problem into a simplified form, where in the particulars of the last example, a transformation of an elastic membrane was transformed from being both a stretch and a shear to just a stretch along the direction of the eigenvectors. So that means that we are actually mostly interested in the direction of our eigenvectors. And this is the reason why amongst the infinitely many solutions that we can have for eigenvectors, we can essentially narrow it down to one by normalizing each eigenvector. So this means that we can work with only the normalized eigenvectors, which we'll denote like this with a little hat, and that's equal to the original eigenvector divided by the norm. So for a particular eigenvector, divided by the norm of that vector. The other important thing to note is when you're constructing your matrix C to diagonalize your matrix A, the order in which you put the eigenvectors is arbitrary. So in this particular case, we put the first eigenvector over here and the second eigenvector there. And we got a diagonal matrix with eigenvalues lambda1 up here and lambda2 down there. If we had instead taken C to be this matrix, then the only change to D is that would have moved the second eigenvalue up here and the first eigenvalue down there. All right, in comparison to this one over here. A very important note is for a matrix A to be diagonalizable, so for an n by n matrix A, it must have n linearly independent eigenvectors. All right, and what this means is any one of the eigenvectors can't be expressed as a linear combination of the others. So expressed mathematically, this says if you have a linear combination of your n eigenvectors, for this to be equal to 0, you must have that all of the alpha ones, all of these scaling factors must be equal to 0 for all of your eigenvectors to be linearly independent. Okay, if a matrix can't have n linearly independent eigenvectors, then that means that it can't be diagonalized. So you might be wondering, if we know that D is a diagonal matrix with the eigenvalues, why do we need hold on. Why do we need to know that we can calculate D by the following transformation? And the reason is because from this equation, you can derive other important results that can yield more efficient ways of computing certain things. So for example, it turns out that D has the same determinant, and you can find it from this, as the matrix A. But because it's a diagonal matrix, it's often easier to calculate the determinant of D. Instead of calculating the determinant of A. And then you can also show from this result that if you want to find the nth power of your matrix, this is equal to the following product of matrices. So you only need to raise your diagonal matrix to the power of C, and then sandwich it between the inverse of your eigenvector matrix and the eigenvector matrix. And because D is a diagonal matrix, the nth power is, I guess, we'll say that there's m entries to not confuse the indices. The nth power of your diagonal matrix D is found by just raising each of the eigenvalues to the nth power. Okay, so this is a much more efficient way of calculating the nth power of A than doing it by hand. So to summarize the last few videos, if you want to diagonalize a matrix A, you first have to solve for the eigenvalues. You then solve for the normalized eigenvectors. You build your matrix C. So your normalized eigenvectors, eigenvalues. You build your matrix C from your normalized eigenvectors. You find the inverse of that matrix. And then you find D by calculating this transformation. All right. In the next video, we'll go through an example with a 3 by 3 matrix carrying out this procedure.